So hello guys, we are welcome back. This is double integration method. That's double integration method to determine deflection of a beam. Okay, so the example I have here is of a cantilever carrying a uniformly distributed load. The question says derive the slope and deflection equation for a cantilever beam carrying a uniformly distributed load as shown in the figure below. Also establish the maximum slope and deflection equation at the free end. Okay, so you derive the equations, then you establish the maximum slope and deflection equation. So let's look at the solution. So the first thing, when you have this type of problem, you draw your free body diagram, okay, or you just redraw the question. So if you redraw it, or you draw your if you draw your what do you call it, free body diagram, you just cut a section X anywhere. You cut a section X. So this is my section X, this is the section X I cut. Let me see, this is the section X I cut here. Okay, so we have our section X cut. That's from here to here is X. Then if we cut a section X from L, then the remaining span will be L minus X. Okay, if you subtract X from L, you will have from here to here. Okay, so the first thing to do is, if you know your sign convention, like the sign convention we have been using is, in the right portion of the section, anticlockwise moment is positive, okay, while in the left portion, anticlockwise bending moment is negative. Okay, so since we are considering the left portion, the right portion, I mean, we are considering the right portion here, which is where we have L minus X. So our moment is going to be negative because of what? Because this load is pushing this moment to go in the clockwise direction, which is against our sign convention. Okay, so it is negative. So we have W times L minus X squared all over 2. How do we determine the L minus X squared over 2? The first thing is to convert this to equivalent point load. So converting this means you are multiplying it by the distance or the span, and the span here, remember, is just L minus X. Okay, so we have W times L minus X. That's the span. Then the moment will be acting half of the span, at the middle of the span. Okay, so if the span is L minus X, then half of it is going to be L minus X over 2. So if we multiply the perpendicular distance and the pause, which is W L minus X times L minus X over 2, you're going to have minus W L minus X squared all over 2. That is why we have in our mx as this. Okay, so we know that mx is equal to ei d square y dx square. So substituting, we have our equation 1 as you see it here. Then integration, you integrate the equation. So after integrating, this is I factored this out because it is a constant. Okay, so we have ei also as constant factored out. So ei integral of the square y and equal to minus w L minus X squared, integral of L minus X squared over 2 dx. So integrating the left hand side, we have dy dx, so the square is gone. While integrating the right hand side, there are different approaches to this. So I don't know if you have covered this in your calculus courses, but this is like, I am equating this to be a number, let's say u. Okay, so if L minus X is equals to u, then integrating u squared, I will have u cube over 3. Okay, so after integrating, because you are adding this, you are adding 1 to this, right? You are adding 1 is n plus 1 over n plus 1. So 2 plus 1 is 3 over 2 plus 1, which is also 3. So we have u cube over 3. Okay, so you need to differentiate what is inside the bracket. Also, you need to differentiate. If you differentiate L is constant. After differentiating, it is 0. X, if you differentiate X, it will be 1. So we have negative 1 here. Okay, that is where we have a minus 1 here. This minus 1 you are seeing. because we differentiated what is inside the bracket. Okay, then for this one, which is L minus x, this is our u now. We substituted the u, which is L minus x power 3 over 3. Why is it 3? Because we have over 2 here already, so 2 times 3 is 6. That's where the 3 is. Okay, so the L minus x over 3 is now L minus x over 6 because of this 2. Then plus c1, which is constant of integration. So which is equivalent to what? W over 6 L minus x power 3, because this minus and this minus are going to give us positive. We're going to have positive. Okay, minus is positive. So to find c1, you can determine your c1 at this point, or you can continue with your integration. Anyone you choose will serve you. So we are going to find our c1 here using the boundary conditions. So for you to know the boundary condition, go back to the diagram. This side, if you look at this thing, you know the conditions. This is a cantilever, so deflection and slope are 0 at a cantilever at a peak support. Okay, at a peak support, deflection and slope are 0, so which means dy dx is 0. So since we have dy dx here, then if dy dx is 0, at what point dy dx is 0? Is at point A, which is x is 0 at A, because this is x, from here to here is x, so which means where x started is 0. Okay, so we have x is 0, dy dx is 0, so we are going to substitute this into equation 2, which is this equation. So substituting here, ei times 0 is 0, w over 6 L minus x is now 0, so we have 0 here for our 3 plus c1. So 0 is gone. We have WL over 6. So WL cube over 6 is plus C1 is 0. So after making C1 subject of the formula, we have WL cube over 6 as our C1. Then you go and substitute the C1 into this equation 2 again. You remove the C1 and substitute it with what you have determined as the value of C1. That is why we are having ei dy dx equal to w over 6 L minus x power 3 minus WL cube over 6, which is our C1. This equation is the slope equation, so you have determined your slope equation now. Remember, the question says derive slope and deflection equation, so we have the slope equation now. So for you to determine or to derive the deflection equation, you just go and integrate this thing again. You integrate it again. So after the second integration, I have ei y, that's the left hand side is now y, dy dx changes to y. Then the right hand side, w is constant, we are going to factor w out. We have over 6 here. Then applying the same principle as we did previously, this is L minus x power 3, so power 3 will be 4 now, because 3 plus 1 is 4, all over 4. So L minus x power 4, that is what we have here, all over 4. The 4 times 6 is 24. That is why we are having 24 here. So we have minus w 24. What about this minus? This minus is from differentiation of this. If we differentiate what is inside the bracket, L minus x, L will be 0 and minus x will be minus 1. So minus times positive will be negative. Okay, that is why we are having minus w over 24 here. Then the C1, our C1 now, which is WL cube over 6, we don't have x here, which means this is constant. So if you integrate a constant, you just introduce x, okay? Because it is assumed that we have x power 0 here, and 0 plus 1 is 1, and over 1. So x power 1 over 1 is x, plus constant of integration, which is C2, second constant of integration. Okay, so since we have C1 determined, we can use the boundary conditions again to determine our C2. Let's go back to the diagram again. This is a pix. This is pix, and at A we said deflection and slope are 0. So y is the deflection. Y is the deflection. So if y is 0, definitely x is also 0. That's point A. So substituting in equation 4, we have ei 0 equal to minus wl power 4 24 minus 0. Okay, why? Because x is already 0, so we remove x. Then plus c2, and making c2 subject of the formula, c2 is going to be positive wl power 4 all over 24. Okay, hence EIY is equal to, that's substituting the value of C2 back into equation 4. So after substitution, what you have is your deflection equation. Okay, what you have is your deflection equation. Now you are done with the first part of the question, that's the slope equation and the deflection equation. You have derived it. Then the next thing is to establish the maximum slope and maximum deflection equation. So we know the maximum slope because this is a cantilever. The maximum slope and the maximum deflection will be at point B, that's the free end. Okay, as the free end. So you are going to use a boundary condition. Okay, since we know that maximum slope will be at the uh, at the at the free end, that's at point B, then at B x is equal to L. Okay, because it means you have exhausted the span. This is x, so if you keep moving to the end of this, you have exhausted the end of the span, so x is now L. So if x is L and dy dx is theta b, substituting in this, remember we are substituting in the slope equation. Here we are substituting in equation 3, which is the slope equation. So substituting here, we have ei theta b equal to w6 L minus x, now changes to L minus L power 3 minus w L cube 6. We don't have any x here, so L minus L is 0, so everything here is 0 now. So ei theta b is going to be minus w L cube over 6. Okay, so therefore ei theta b is minus w L cube over 6. Hence our slope divided by the coefficient of theta b, we have theta b to be equal to WL cube over 6EI. This is the slope. This is the slope equation. Okay, so the next one is the deflection. The maximum deflection also is at point B. So using the same boundary condition, at B x is L and y is equal to YB, which is the maximum deflection. Then EIYV, substituting in equation 5 now, the deflection equation. Now we are substituting in this equation here, where we have minus w over 24. So minus w over 24, this is x, we replace it with L. Here we have x also, we replace it with L. Here we don't have any x, so we don't need to write anything. So L minus L is 0. This one now becomes 0, and this changes to L power 4, and this is L power 4 also. So you add the two, you take LCM. I think the LCM will be 24 since. So if you take the LCM, 6 will go into 24, like how many times? That's 4 times. 6 in 12 is 2, so 6 in 24 is 4 times. So we have 4 times 4 minus 4 plus 1 will be minus 3, so minus 3 WL power 4 over 24. So to determine our YB, we just make it subject of the formula by dividing by its coefficient. The coefficient is EI. So 3 can go into 24 8 times. Okay, so we simplify this. We have YB to be equal to minus WL power 4 all over 8 EI, and this is the deflection at point B. So with this, you are done with this question. Okay, so if you have any question also, you can drop it in the comment section. So this is where we are going to stop till we meet in the next video. Thank you.